Okay, so let's take a look at this bad guy. Applications of partial derivatives. We're doing error and approximation. I checked my textbook. I feel there was another application, but let me see if it's something we need, and I'll have to make a video on that. But okay, let's x be a function of two variables, x and y. So x is a function of that. I don't know why I keep on doing this stuff. I should just put let z be a function, then it is expressed as z is equal to f of x comma y. Suppose there are changes in x and y. Let the changes be denoted by delta x and delta y respectively. Then the changes in z is represented. So z is a function of x and y. If x and y changes, then there will also be a change in z, a corresponding change in z. So now that change in z is given as partial z over partial x delta x plus partial z over partial y delta y. This is kind of like total differential, just that we're using delta now for where we had normal d. So for z, a function of x1, x2, x3 to xn, we have that we have it to be delta z is equal to partial z over partial x1 delta x1. It keeps on going. So this is like a general formula for the z and delta z rather. It keeps on going to delta z over delta xn, sorry, partial z over partial xn delta xn. Sorry about that. Okay, so let's take an example. So the deflection y at the center of a circular plate suspended at the edge and uniformly loaded is given by y is equal to kw d raised to the power 4 over t raised to the power 3, where w is the total load, d is the diameter of the plate, t is the thickness. Okay, calculate the approximate percentage change in y if w is increased by 3%, d is decreased by 2.5%, and t is increased by 4%. Alright, solution. Quickly, we know the formula, we just apply the formula. We are given three variables now. So y is a function of w, d, and t from the y is a function of k. Okay, k should be a constant. So y is a function of w, d, and t. Yep. Okay. So we state the formula. Delta y is equal to partial y over partial w delta w plus partial y over partial d delta d plus partial y over partial t delta t. Now, this is what we have. I had to write it down so that when we differentiate, it won't really be foul, so we just know what we're differentiating. Although I think I still made some mistakes again because I was looking at this one when I wanted to differentiate this. Now, partial y over partial w, and then maybe for you, I would suggest you put it line by line. That's what confused me here. So partial y over partial w is here. So differentiate this with respect to w. This is kd4 over t raised to the power 3. Partial y over partial d is going to be 4kw d raised to the power 3 all over t raised to the power 3. Now, partial y over partial t is you're going to use quotients. So you have t raised to the power 3. Differentiation of this with respect to t is 0. That's what I did. So this v du dx minus u. Okay, so I was actually looking at this one. That's why you have 4 here. So minus u. This is your u times differentiation of this with respect to t is 3t squared all over v squared. That's t raised to the power 3, everything squared. When you open this, you're going to have minus 3 kw d raised to the power, is this 3 or 4 now? This is 3, 4, sorry. Alright, so these minus 3 kw d raised to the power 4 t square all over lots of indices, the powers they multiply each other, all over t raised to the power 6. Now t raised to the power 2 can cancel 2 from the 6 here, so Your final answer is minus 3 kW d raised to power 4 all over t raised to power 4. So we've gotten differential of y with respect to w, gotten differential of y with respect to t, and we've gotten this we've gotten differential of y with respect to t, and we've gotten differential of y with respect to d. 1, 2, and 3. Alright, so now the percentage change in w is denoted as delta w is equal to 3% times w. That's 3% is like 3 over 100. 3 over 100 times w equals to 3w over 100. Percentage change in d, which is delta d. Delta d is equal to, is a decrease. They said d decreases by 2.5%. Yes, I can see here. Decreases by 2.5%. So you have minus 2 raised to power 1 over 2% times d, which is equal to minus 1.5%. So minus 1.5 d over 100. I don't think you need d over 40. You see the method solution because we are talking about percentage change. So you see it. Percentage change in t denoted as delta t is equal to 4.5% times t, which is equal to 40 over 100. Alright, solving for percentage change in y. You know the formula. The y is equal to partial y over partial w, delta w, plus partial y over partial d, delta t, partial y over partial t, delta t. This delta d, delta t. So you just bring in those different values we were able to solve for and put them in the equation. Fun facts here. So even when I was solving, I was like, oh, it's true. So what do we do? You're giving your y in this format. Y is equals to kw d raised to power 4 over t raised to power 3. This is kind of like the value of y. They didn't give you a numerical value of y, neither did they give you values of d, or neither they give values of w, d, and t. So you can substitute to get the exact percentage change. So what do? You leave your y in terms of this with the percentage change. That's how the final answer is. So that's what I did here. W times this is going to give you k w d raised to power 4 over t raised to power 3. I brought it out, the y now. I put it back in this form. This is the percentage change minus, put this one too back in the original form with the percentage change. Be careful, I did 5 over 2. 2 cancel the 4 here. You're left with 2. 2 times that 5 will give you 10. The minus multiplied by this plus, that's what came about the minus here. So you have 10 over 100. Put this one back. I sent the 3 inside, brought out the minus. You have k, okay, the t also cancel the t over 4 here. So you have kwd raised to power 4 over t raised to power 3. So we can now factorize out kwd raised to power 4 over t raised to power 3. We factorize it out, then we put this in a bracket. We solve for this, and this is what we get. So delta w is equal to kwd raised to power 4 all over t raised to power 3 bracket minus 19 over 100. This is just one of the ways you can apply it. So it was also new to me then, like, okay, so you can actually do stuff this way. So that's the essence of getting experience, essence of solving questions, different questions. It opens your mind to different possibilities, and it will help you a lot. So now the result shows that y is decreased by 19%. So that's what we're saying. So this is the answer. They say you should show the percentage change in y. So y decreases by 19%. That's the change. And then we have one more question here. The power P dissipated in a resistor is given by P is equals to E square over R. E should be basing the EMF of voltage now. You guys know it. If E is equal to 200 volts and R is equal to 8 ohms, find the approximate change in P resulting from a drop of 5 volts in E. Okay, resulting from a drop of 5 volts in E and an increase of 0.2 ohms in R. So you're giving P to be E squared over R room. You're giving numerical values of E and R now, different from the other one. And then it says you find change in P when there's a drop in this in voltage, a drop of 5 volts in E. So this is your delta E, and an increase, a drop now should be negative, then an increase of 0.2 ohm in R. So that's positive 0.2. Alright, solution. P is equal to E squared over R. Now we want to get the first value of P, since there's a given volume. So before we get the change, let's get the original value so that we know how much it changes by. So now P is equal to 2000 and 200 raised to the power 2 all over 8. When we substitute it into this, you have 40,000 over 8. That's 5,000 watts for power. We're talking about power. So your SI unit is also still important. Delta E now is minus 5 volts. Recall there is a drop. And then delta R is 0.2. There's an increase, 0.2 ohm. So delta P is equal to partial P over partial E, delta E plus partial P over partial R times delta R. Now delta P over delta E, from the relationship here, differentiate this with respect to E partially. You have this to be 2E over R. And then differentiate R. Differentiate this partially, you have minus E squared over R squared. Kind of when you're doing Y over X. If you're setting this with respect to X, you know it's going to be minus Y over X squared. So here it's just minus E squared over R squared. I think that's what I thought of first. So put this into the formula. We have 2E over R minus Y plus minus E squared over R squared 0.2. Open the brackets. This is what you have. Where E is equal to 200 volts. Okay, from here now, from here we put in the values of E to be 200 and R to be 0.2. That's what we did here. You get your delta P, Our final result shows that delta P is equal to minus 375 watts. So when there's a drop of 5 volts and an increase of 0.2 ohm, the change is that the power decreases by 375 watts. Like the power decreased by 375 watts. So that's another example of application of partial differentiation in errors and approximation. Alright, so be sure to go through it and ask your questions.